Good afternoon. Is the slide visible?
Yes, sir.
Okay. So, what we have discussed yesterday, the last day actually, that is the linear SVM. So, a quick recap of the linear SVM is that this is the that we have a classifier like this, something like that, and what we try to find out, that is the kind of flat margin, and these points are basically helping to find out this margin. Okay, and it's called the support vectors. These points are called support vectors. And what we are trying to maximize the margin width. So we calculate the margin width as 2 by the W norm, and we try to maximize it. Maximize this M. Maximum, this is M actually. So this we try to maximize the M. So that was our formulation. And we have shown how it is 2 by W as norm by this thing. And then we frame our this optimization problem in this way, that maximize the margin as same as minimize 2. So actually this maximization of this is similar to the minimization of that. And we formulate our quadratic optimization problem, that is here, problem to solve for W and B. So this is our, we have to minimize this half of W transpose W transpose W, and with subject to yi wxi plus b greater than equal to 1 for all I. So this is a constant optimization problem. And then we have to solve this problem. So that we'll start today. how to solve this. Now we to formalize this problem in this solving this optimization problem. For find W is a vector, and this B such that this IW is half of W transpose W, and that is to be minimized. Subject to the constraint that all of xi and yi, these are the data samples, yi of yi and multiply W transpose xi plus b greater than is equal to 1. Now, one thing is very, you have to, I think, I assume that you understand this, why it is this. I think all of you. So all of you know that, or you have any doubt? Why from where this W, yi, W transpose etc. Because this is, you may, somebody, if you don't understand why this particular constant is coming, then it will be problematic for us to formalize the problem. So if you have a doubt, then I will again say, otherwise you continue. Okay, so anybody have any doubt, please ask why, from where this come. Huh? Yes? Hello? Okay, so I assume that everybody will at least recall this, and how, from where this is coming. So now I read out this because this problem we have to formalize bit differently. So this is a optimization, convex optimization, quadratic optimization problem that this convex quadratic objective function to the subject to the linear constant. So this constant is basically a linear constant, but it's basically a convex quadratic optimization problem. So quadratic optimization problems are well-known class of mathematical programming problems and can be solved using the quadratic program. So that is up to that it is okay. Now the solution involves constructing a dual problem that we'll formalize. That try to find what is dual problem at where a Lagrange multiplier alpha I is associated with every constant in the primary problem. So there is the primary problem. We have to define what is the primal problem and try to find out this dual formulation. Okay, so but before going to solve this particular problem of this linear support vector machine, we try to understand what is the mean by Lagrangian duality or Lagrange duality. So Lagrange duality is get to the optimization problem in dual form. So allow us to use the kernels to get optimal margin classifier to work efficiently in every high dimensional space. That we'll see later. And allow us to derive a very efficient algorithm for solving this above optimization problem. So first we'll see this, okay, and then we go for this. So first of all, this problem, this is a two-way of solution, okay. So this one to use this kernel function is called kernel trick to project these data points. So this is the basic this thing. If there is some problems, is that these data points we can project to a high dimensional space. Okay. So you have to project in a basically to a high dimensional space, and so on. These are the dimensional space. That is the how much the nonlinear kernel we have to use kernel function to mapping from these points to that points. And this is one strategy. Another strategy of solving this optimization problem. So first we'll see this how to do that. So what we start to understand what is called Lagrangian duality. Now let we have to for formulate problem. Let this is f of w. This is your optimization problem, that objective function. And that we have to do, we have to calculate the minimum of w of this function, objective function, subject to the constraint of there is another function giw that is it is on normal inequality function. So there is a some less than greater than thing. So this is called inequality condition is equal to 1 to k. And another is h1w. It is called equality condition. That is I is equal to 1 to k. Okay, these two things. So this is a very kind of standard formulation of any function that we have in this format or in this set. Okay. So this is the problem we have to. This is the primal problem, the main problem you can say. Now, if we formulate the Lagrangian duality or that just express this problem using this Lagrangian dual problem, then this is called the Lagrangian function. Okay, this L of W alpha and beta, and these alpha and beta are called the Lagrangian multipliers. Okay, how we formulate that is the main primal function fw plus summation y is equal to 1 to k. This summation is because this I is basically 1 to k, so this is 1 to I is equal to alpha I. So alpha is basically a Lagrangian multiplier index, and giw because these are the different instances. So giw. Okay, and I is equal to 1 to L. This is 1 to this is L. So this is 1 to L, bi, beta I, H I W. Okay, so this is the, you can say, the Lagrangian formation. Formation with Lagrangian multiplier. So constant, this is a constant. Now it is becoming unconstant. There is no constant here. So with these two constraints we put, so it's a kind of, you can say, bit simplistic way to say that this particular problem is called that how to convert or express a constant optimization problem with unconstant optimization problem, because this particular formulation has no constraint, but here is a constant. Understood? So this is the some way of handling this kind of problem. Okay, so this is the formulation, problem formulation. Okay. Now, how to solve it, we'll see later. See later means, yeah. Okay. Now, this is called Lagrangian duality. So, Lagrangian duality, there is one lemma. That lemma is said that maximum of alpha, beta, and alpha is greater than 0. These are these Lagrangian multipliers. This L, this problem, so that way to express, is equal to the primal problem. Now, FW is a primal problem. That you can see that FW is a primal problem. This is FW is equal to FW if W satisfies the primal constraint. What is the primal constant? These are the primal constants. If this primal W constant, this primal constraint, then this W satisfies this primal constant, then this equation maximum of this L function is basically the f of W. Otherwise, it's infinity. Okay, if it doesn't satisfy primal constraint, it's infinity. So this primal problem can be rewritten in this way. Now you see that if W satisfies this primal constraint, then it is FW or this. So this particular function, if you take the minimum of this, so this is the maximum of this. So if you take the minimum of it, obviously this is the minimum, because other thing is infinity. So we have to calculate the minimum of W of this function, and that function is basically defined in this way. Okay, so that for W you can to find the minimum of this. So mean W, mean max, basically mean W and max alpha beta. So of L of alpha W alpha beta. So this is the just a dual formation of that. Okay, no, it's not a dual formation. It's just a lemma. And what is the dual formation? So the primal problem is this. Now we say the primal problem is a P star. That is mean of W, because this is what we calculate. Mean of W, max of alpha beta, and alpha I greater than equal to 0 is called, this is the primal problem P star. And it's dual. Now it's a dual formation. Now dual is that you just swapping these two things. That maximum of alpha beta, alpha y0, mean of W is equal to L of this, L W. So this is just a dual formation of P. Okay? And now there is a theorem. It's called weak duality theorem. What it basically going to say that this, if this we do, then this P star, that means this particular P star greater than is equal to D star. Okay. So that is in general greater than is equal to D star. And if it is equal to D star, if there exists a saddle point. Saddle point means what? When these two are, so actually saddle point is basically reversely defined, that the strong duality constant, if and only if there exists a saddle point when this equal point of L of W alpha beta, then we have D star. So this is the dual formation. This is basically actually this is the the theory of convex optimization. This is the theory of convex optimization problem. Okay, that's what we are saying. This actual proof or the actual thing is beyond of the scope of this class, because we there is a lot of kind of optimization theory or this kind of materials. So the thing is that if you really interested about it, that this some result we are basically taking from the optimization theory. Okay, so these results are good enough to just you have to remember this result so that you can use this result to solve this your problem, and that is very important to solve you. So the thing is that, and if you really want to know that what is the underlying theory or underlying proof, you can go and any optimization kind of book, then you can get it. Okay. Okay. So now there is a one important condition. This is called a KKT condition. What KKT condition is saying? If and only if there exists some saddle point of this, okay, then it satisfies the Karuskun-Tucker condition. What is this condition? Condition is that the derivative of partial derivative with respect to wi of this term L of w is equal to 0 for I is equal to 1 to k, and dd of bi, this of bi means basically differential of with respect to bi of w alpha b is equal to 0 for 1 to l. So if we formulate these two things and some sort of mathematical manipulation, we find alpha I gi w is equal to 0, gi w is equal to less than is equal to 0. Now definitely if it is alpha is equal to alpha is greater than 0, then this is basically if alpha is equal to 0, then g is less greater than is equal to 0. So the what is the theorem? If W star, alpha star, and B star satisfy the KKT condition, then it is also solution to the primal and the dual problem. Okay. So the what is the basic understanding is that for our this W and for the W, if it is called W star, if it is called alpha star, and for B star, this is some special alpha W alpha beta. If they satisfy this KKT condition of these conditions, then it is also solution to the primal and the dual problem. So primal problem and dual problem will be solved. Okay, so this is the of this condition. This is also a result. Okay, so with this background, with these results, that these things, the proof is, I already said, it is beyond of our course of this discussion. Now, with this result, what we have to do, we have to formulate our linear SVM problem. That is also a constant optimization problem of this sort. Can it be possible to formalize this linear SVM problem to solve this problem, to actually to solve this linear SVM problem as a to make it a constant optimization problem using Lagrangian multiplier, and how to solve it? Okay, so then let's see. I try to understand this. Now again we come to our problem formulation, that our we have to find W and B such that we have to, this is the our basically half of W norms, that is half of W transpose W, that should be minimized. So we have to minimize W. and this is the constant xi yi and yi is into wt. Just a second. So this is optimization that we said this is a complex optimization is already we have shown that we have. Now how to frame this particular problem to this whatever this Lagrangian dual formulation problem. So now our primal problem is minimum of WFD, FW, and generalized Lagrangian is this basically Lagrangian multiplier. So duality of SVM. The primal problem is this. So in this way we can basically try to find out, okay, of alpha is equal to alpha is equal to b, beta is equal to Lagrangian. We don't have the equality constant, so we only deal with this alpha is. Okay. So for our case, this is okay, and this there is inequality as this particular. So let's try to understand. Okay, if there exists a saddle point, this particular is like this. Now, if we give this particular equation, so what is our FW? This is FW, or we can say this is our FW. And what is our GIW? GIW is basically uh, YIWT transpose XI. So this is our constant. So we can put it in this formulation. Okay. So if I put this is our actual uh, for I is equal to 1 to m. If m is the number of samples, this is the kind of formulations. Okay. So this is the and this actually copied from that particular slide, but actually this formulation we will do with respect to our SVM problem. And if we say just if I coming into this problem, the support vectors is those. So if alpha is equal to, if this is the condition and this is equal to this, so if alpha greater than 0, then g of w is equal to 0. Only a few alpha is are non-zero, so that is important. Only a few alpha i's are non-zero, and these non-zero alpha i's are our support vector. Okay. So the training data points having non-zero alpha i's are called the support vectors. Now this is the actual formulation of this. Now this is the formulation. You can see that this actually is our problem. So if we put a Lagrangian function out of this support vector definition, so minimize LP WB alpha I. Now this is WBB of this is B and alpha I. Half of W square, this is our FW, and minus this is summation I is equal to 1 to n, n is number of data points. And now this, we put this, what is our constraint? So alpha I, yi, w transpose xi plus b minus 1. Okay, so this is our, now we actually put our this SVM quadratic optimization problem with linear constant to this Lagrangian formulation. Okay, and switch that so that alpha is greater than or equal to 0. And where P denotes the primal, so this is the P actually. So this is the primal problem. Okay. Now this is the most important formulation that minimize LP of this. If you understand this, if you say that, okay, sir, it is okay. Now this particular formulation is the SVM formulation of this formulation, because this part is not there because we don't have the equality condition. Only this part is there. So these two part is being actually given. This part we don't give. This part is not there. Okay. So that thing we have here we put in this formulation that minimize LPW alpha I is, this is omega, this is W square or W norm actually in this. Okay. So if you have any question or any doubt, you can ask. Okay. So now it is trying minimize LPWB alpha I, that half of this of, and this will put in this format. Now minimizing LP with respect to W and B with a fixed alpha, that we do this basically this theorem, we do this differential equation with respect to W and respect to B and equating to 0. It gives W is equal to I is equal to 1 to n alpha I yi xi. Okay, and this is equal to, so this summation of I is equal to n alpha I yi is 0. Okay, so these two things we can get equating these two, taking the differentiator of this as we have done here. This is two things we have done. Okay, it's exactly two things we have done. Okay, and we get this equation of this three equation. Corresponding equation for our formulation is basically this and this. Now you know W. Now if we put W in this equation, now this is our alpha I, this is LP equation. What is our LP equation? This is our LP equations. Now this is the W, and there is a some these equations. If we subtract this, we replace W in this equation, what it will look like? Now this is I is equal to 1 to m alpha I. Now this is called alpha I here. We say W is equal to this alpha I. Half is equal to 1 to j, I is equal to 1 to n alpha I, alpha j, yj, and xi is transpose xj. So there is some mathematical, some sort of thing I just imitate this one. And minus b of summation I is equal to 1 to m alpha I yi. So this is basically our formulation of LP, the Lagrangian formulation, dual formulation. And if you just take this as alpha yi is equal to 0, that you see alpha yi is equal to 0 here, this particular thing, then if we put alpha equal to 0, so this term is basically 0, and we can find I is equal to 1 to m alpha I minus 1 by m, I is equal to m alpha I alpha j yj xi transpose xj. So this is two vectors. Okay. So this is basically our formulation. This is our Lagrange formulation. Now, this is our Lagrange. Now we have to put our dual formulation. What is this? Is the primal formulation. What is the dual form of this? Now we have to follow in the dual optimization problem. Then max alpha of j alpha is equal to this, and so that alpha is equal to greater than 0, I is equal to 1 to k, and I is equal to 1 to m, alpha y is equal to 0. So this is a quadratic programming problem. So this is our dual problem. So a global maximum of alpha I can always be found. So this alpha I can use in this particular problem, because you see we have to find the minimum of this, so we have to put the dual formulation. So max alpha of j alpha. So this is the maximum. This is the dual formulation. This is the quadratic programming problem, and global maximum of alpha I can always be found from this particular. Okay. So once we have Lagrange duality for alpha I, alpha j, we can reconstruct the parameter vector W as the weighted combination of the training sample. So what we can say, that if I can alpha j, then W is equal to I is equal to 1 to m alpha y xi, W is equal to this I. Now this I actually, those i's are actually important. This I is equal to 1 to m. M is total number of samples. But if those I is basically the support vector, that will going to take. So summation over only the support vector. This has been support vector. Okay. So alpha yi xi. Okay. These are the important of, and which only not for all samples, only for support. Now, if a new data is come, let's say new data set has come. So what we have to compute? We have to compute W. Now we know the W, WTZ plus B. Okay, and that what does this mean now? That with the support vector, I is equal to support vector is B, alpha I, yi, xi transpose Z. Now this is important. This xi transpose Z, that particular thing, because plus b, that is the this b, and classify Z as 1 if the sum is positive and is class 2 otherwise. Now this is very important here, because this particular thing, because this can be used as a dot product of xi, sorry, dot z is a kind of another point. So it's a vector, it's a point. It's a point vector actually. So these two things. So this dot product. Okay. So the computation complexity is becoming very less, because if you know only the support vectors. Okay. So if the sum is positive and class 2, otherwise W need not be found. W need not to be found explicitly. Now this W is not required to found. This W vector is required. Now, only this, within these things we can try to understand that this particular Z, that is the data point, to be classified, it is classified using this XIT, and the corresponding Z with this alpha I and yi. Okay, so that is the major advantage of the SVM, that because this dot product is a very computationally efficient. So that is one of the major observation of this particular sort of problem. Okay. So the discriminant function is this, is the discriminant function of a support vector machine, of a linear support vector machine. You can say I is equal to becomes this wxt, because you know that is what is wx. What is wxt? This wxt is this. This is wxt, because this is actually the your y. This is, now if it is greater than some, for some w a wtz plus b, if it is greater than 0, it is positive, and it is greater than WTZB plus B is less than 0, which is negative. This is the formulation. Now what we find? We find that this value, then we have to understand W. But we don't have to understand W. For the sake of these support vectors here, let's say this is the support vector. This is the support vector. So we can get this kind of fat margin. If we know this support vector, then this W is replaced by I is equal to support vector alpha I. This alpha is Lagrangian multiplier xi. Xi means these data points, this support vector xi, and x. X is the new. This x is basically this. That should be actually x means now it is, if it is z, becomes z plus b. So xi plus this. This is the dot product of xi and this. Okay. So it realized that a dot product between a test point and the support vectors. You can say these excites are support vectors. Excites are support vector. And z means some x or something. This is your point. That is sufficient with presence of this alpha I to get. That is the function. Solving the optimization problem involved computing a dot product of this between all pair of training points. It's scalar value. Okay. Optimal value of W linear combination of small number of data points. W is a linear combination of small number of data points. So that is definitely. Now you understand what is the essentiality of SVM, that how actually only not considering all the data points, only considering the support vectors, we can find the easily that any query point or any novel point that will be in which side of this decision. Okay, so any question you can ask? Okay, so the dual problem, now we have the following dual optimization problem, that max of alpha into j alpha is equal to m alpha I minus half of this alpha I alpha j yi yj xit xj. Okay, with such that alpha I greater than is equal to 0 and I is equal to 1, and I is equal to 1 to m, alpha I is equal to 0. This is quadratic programming problem. And a global maximum of alpha I can always be found. This is the basic idea. This is the dual problem. So that is basically the basically idea of SVM, where the major thing is that if there is exist a linear separability, so there is a linear separability between these points. Okay, so that how things can be using just this dot product. Okay, now if I say so, it is okay for any questions of that, because a lot of things we have with mathematical involved thing. Really, we are not deriving anything, just we use some kind of results from convex optimization theory. So any questions? Now, if you understand this, if I say that okay, this is fine, but there is a point here. Now, how you tackle this kind of outliers in this kind of SVM problem. If this is not, definitely this particular problem is not, this is there. So this is your kind of this, and there is some sort of fat lines also there. If there is a problem here, then how you handle this particular problem? Or another thing we can ask. If this kind of thing is there. So how to solve? This is not a linearly separable. This is not. So this question is not solved. Because in this particular, this is a two-dimensional space. This is only the possible curve decision boundary. Okay, let's see. Now this problem, now we said that what is the assumption of this, whatever formulation, linear formulation we said, this is the basic formulation, that alpha q of alpha I minus half of double summation alpha I alpha j y j x t. This is the dot function, dot product, where alpha is equal to 0 and this. So this should be maximized. So this is the dual formulation. But assumption is very important. These examples, for training examples, are linearly separable. If this is okay, this is assumption. And this is sometimes most of this very unrealistic assumption. It's not very practical. What? Now, this is the case. What if data is not linearly separable or noisy data points? Now, extend the definition of maximum margin to allow the non-separating planes. The question is that how we try to find, in this case, how we find this concept of SVM. Okay, so this is the problem. This is the problem we had currently at our hand. What about noise data? So the solution has the form, this as of now, whatever we have solution, this W summation alpha yi xi b is equal to yk minus W transpose xi for any x k such that this alpha k are not equal to 0. That we have seen. Each non-zero alpha indicates that corresponding xi is a support vector. That is also said that non-zero alpha is basically that. The classifying function will form this. So that is most important thing. That if a new point z come, so this x is basically a new point, that is any point z, and thus we just calculate the summation alpha I that is known yi, and this summation xit is a training sample dot product. Here it is x, that means it is z. So this actually we have to notice that it realize that inner product between the test point x and the support vector xi will return to the, we will return to this letter. X and support vector is the the inner product between. Also keep in mind that solving the optimization problem involves computing the inner product is between all the pairs of training points. So only problem involves computing the inner product of this all the pair of training points, but it is only the kind of support vectors. Okay. Now we extend this idea that with data set with noise. Okay. So far, what we have discussed, this is the idea. This is called hard margin. Even if there is a kind of margin of this. Okay. Now, what if no training error? Your data, the training, if this hard margin classifier assume that there is the training sample, what is been given is a noise free. Okay. But if training set is noisy, then what? Because this function, you see, this suppose is not supposed to there. This function is not supposed to there. Okay. So this is kind of solution will use the very powerful kernel. So the kernel will use the later. That kind of thing you can use. So this is a problem of overfitting kind of. Okay. So this is the idea that if okay. So we stop here today. You just think about it that how we are going to solve it. This particular problem. We'll continue this lecture. Tomorrow is again the Friday running. So we'll meeting tomorrow again. Okay. Thank you.